Good day, everyone. Today I'm going to speak with you about additional mechanisms. So these are going to be mechanisms that are kind of going further into what you've learned from a previous chapter with SN1, SN2, E1, E2. Instead of focusing on the actual conditions, we're just going to focus on the reagents themselves and see what kind of transformations we can get out of each particular example. So this is going to be particularly important when we start thinking about synthesis and how to properly transform things from point A to point B to point C, etc. Okay, so we'll start off with this particular example where we have a very stubborn leaving group that we're going to make a very formidable leaving group. Okay, and we're also going to pay attention to stereochemistry here. Okay. We're going to treat this with PCl3, which I will forget the lone pairs, but just note that that phosphorus in the middle is getting electrons tugged away from it by the chloro groups. Okay, so we're going to have this as our product. Oh, that was not very nice. Okay, so an inversion of configuration, as you see here, from reactant to product. Now, one thing to note is that try to think of which is going to be the electron-rich group and which one's going to be the electron-poor group. So oxygen is going to be electron-rich, meaning that it is going to attack with its lone pairs this phosphorus. And as a result, one of these chloro groups is going to fly off. Okay, so having this charged intermediate now, so in other words, you've already kind of initiated some sort of charge separation. Oh God, this is ugly. Okay, with positive charge on that oxygen, PCl2. I'll wipe that off. Okay. And then remember that Cl minus that left is now going to behave as a nuke. It's going to remove this oxygen. Now, word of caution here, so it's going to have to attack from the backside of the board to knock this off. Just word of caution that only primary and secondary alcohols are going to work for this particular reaction. Okay. Just think about some kind of carbocation stability. If you were to, say, have all this transpire in SN1 conditions, it's not really going to be likely. Okay, and also you're doing an inversion of configuration, a stereospecific product, so that's something also to be mindful of. Okay, so this is the conversion you're going to get, and you're also going to have POH Cl2 as a byproduct. Okay. So the next thing we're going to talk about is some kind of nucleophile that is kind of rogue in a sense because it doesn't really have the control that you would see with some of the other nucleophiles that we've gone over. Okay, and that's primary amines. So primary amines undergo some kind of charged state intermediates, where say we take ethylamine and we introduce ethyl chloride. Okay, so we have a positively charged group which would be stabilized by that Cl minus, but we're not going to worry so much about that. Remember that amines can also act as weak bases if the lone pair is still there. So this is a quaternary amine. So this is going to be behaving as a base to neutralize this particular secondary amine now. So every time you add an alkyl group onto that nitrogen, it becomes, primary, secondary, tertiary, and so on. Now, is this going to stop from one particular reaction or with one particular substrate? No, it's not. It's actually going to be successive, because if you see right here, this is a positive charge that I had. So that would be stabilized the more alkyl groups that you have about this nitrogen, right? So remember that alkyl groups are electron donating, so you're going to feed some electrons in there and kind of stabilize that nitrogen's positive charge. Okay. So just from a practical standpoint, amines are not very wonderful to work with, especially if you have to get a pure product. So trying to distill this would be a nightmare if you had secondary amine, tertiary amine. Right? And then even some quaternary amine. And then you're pretty much locked up from there. You can't really go backwards. Okay, so the next example I'm going to give you is a tale of two bases. Okay, so we have LDA, or lithium diisopropylamine. Oops. Try again on lithium there. And then we have potassium tert butoxide. Okay. Now, then we have one substrate, but we have two different sites where alpha hydrogens are protic. Okay, so if we have a very bulky base like this, and we, let's say, deprotonate or form what is referred to as an enolate at low temperature, we are going to remove a hydrogen at the most accessible point. So notice how it's more accessible than any of this. I guess something would be just as accessible over here, but nonetheless, you have a really bulky alkyl group, two substituents right there about this business end of the nitrogen. Okay, so the nitrogen is going to act as a very strong base. Take a look at the pKa in your chart. I think there's this equivalent. Should be somewhere close. Okay. Now, ignore that for a minute. So if this hydrogen is removed, coordinated to a very strong base like that, you're going to have resonance structures. So enolates are essentially going to be some kind of resonance form. Okay. So this is going to be the kinetic enolate because it's going to be at low temp. That is very important. Okay. And this is going to be the most effective resonance hybrid at low temperature. Again, this is going to remove this hydrogen the fastest. So in other words, this really has no time to go around and try to, fight through all these other methyl groups to take up this hydrogen that's over here, for instance. Okay. Now, if we look at the other base, the second tail, we see that we have fairly strong base, not quite as basic as lithium diisopropylamine, but nonetheless, it has a little bit more access, even though that's a little bulky there. But this business end can come around, take this hydrogen up, and lone pairs go in. Now this is going to form what is referred to as the thermodynamic enolate. This will be at higher temperature, not quite suggesting that it's going to be boiling or anything, but higher temperature. Okay, and then you would have maybe a conjugate acid to this as your solvent or something. Nonetheless, you're going to have a thermodynamic enolate, which, if you don't mind me erasing, I'm going to switch this up. Let's see here. Okay, so now instead of having my kinetic enolate like what's here, by the way, this kinetic enolate is going to attack, it wasn't just a means of deprotonation, sorry, it's still a little early here. Let's say we have some kind of electrophile that's reactive, okay, and then we throw our electrons down. I'm going to come and knock this chloro group off, and then you'll have quite see that. There you go. Okay. So that's the type of product you would form through a kinetic enolate. Now, a thermodynamic enolate, you would form this. This is kinetic. This is thermo. The way I keep straight whether something is thermodynamically stable or kinetically stable is really the temperature. If it's temperature driven, that means, and it's also a selectivity of base. I would think that less bulky, higher temperature is going to be thermodynamic. Low temperature, bulky base is going to be kinetic. Okay, so this is another type of alpha connectivity. When I refer to alpha, I'm saying a carbon that's alpha to a carbonyl. So this side's a dead end because there's no hydrogen to remove. Okay, so in other words, we're forming enolates again, albeit in somewhat different fashions here for the bottom and top particular examples. One's going to be under basic conditions. Okay, and then the other is going to be under acidic conditions. So I'm going to show you the first steps involved here. Okay, so different mechanisms. One pair. Okay, so you have your enolate, which again is going to be resonance stabilized with these lone pair electrons dropping down, kicking them out to the alpha carbon, etc. But one thing of note here, so these Br2 molecules are going to have an instantaneous dipole at some point. So you don't think of this as your typical electrophile, right? Because these are both electronegative atoms or elements. However, same element, whatever. We have, let's say there's a partial positive and partial negative. Okay, so this is basically a swaying back and forth of electrons. All right, so these electrons come down and coordinate. It's going to boot that Br minus off. Okay, so this is going to be kind of electron starved because this is taking some electrons with it. Okay. Okay, so let's look at one of the products, or this product here. And then, so this will be R or S. Something I failed to mention on the last particular example, that when you have enolate chemistry, sometimes you're going to get R and S configurations depending on if there's some stereospecificity. In this case, there will be. Okay, so you have RS, racemic mixture. Again, when I do a racemic mixture, I just do a squiggly line. Okay, and okay, so now if you're under these same conditions, right, you can actually brominate this not once but twice, because you still have that other hydrogen hanging off of there. Okay, and this hydrogen is directly connected to a carbon that has electrons being tugged away by this electronegative CO double bond, as well as this bromo group is going to be even more acidic. Okay, so if you're still under basic conditions, this hydrogen is going to get stripped again, and then the process is going to repeat itself. Okay, so 2 times you're going to get alpha bromination twice. Okay, so that's not going to be stereospecific. It's 2 identical coordinates. Okay, now for the bottom example, I'm going to shorthand this with pH because it takes forever and mine are ugly anyway. Okay, so pH here. Okay, so we have a positive charge about that oxygen. Not exactly a no-no, but what that oxygen is going to do is draw electron density away from, especially being positively charged, away from this hydrogen. So either this is going to be acidic or this is going to be acidic, right? So this is probably going to bounce back and forth in equilibria, no big deal, but the only way we can get things to proceed forward is by having water act as a base, right? So in other words, there's too many lone pairs. Water is acting as a proton transfer initiator. Okay. Now, So this isn't necessarily an enolate, right? Because it's under acidic conditions now. But if we push some electrons and again hit this Br2 that has some instantaneous dipole to it, we're going to see that we have alpha bromination again. Okay. But here's the here's where things stop is upon additional bromination, it's not going to happen. It's going to stop here. Why? Because this positive charge is going to be in competition with this Br. Okay, so that's going to be kind of an issue. When you see this enolate above, you can see that, you know, if there's, let's say, one enolate, or sorry, this this negative charge here with a double bond, and then let's imagine there being a bromo group here. That's not quite as bad as this being electron starved and this bromo group pulling electrons down. So in other words, this is going to be destabilizing this positive charge even more. So in other words, this is going to be way more acidic. In other words, you're not going to see anything beyond alpha bromination just one time. Okay, so the last few examples I went over with you were, at least with the enolates, those were all what you would consider forming some kind of nucleophile in situ or in the situation. Okay, so this is going to be kind of no different. When I say in situ, that means that this isn't something that you can necessarily dig out of a bottle, right? So something that's you have to prepare by adding two things together and making something else. Okay, so let's take another example here. Now this is what is referred to as methylation of a carboxylic acid group. A functionality you haven't been very well introduced to up until this point other than proton transfer. Okay, so as you can see here is an acid. Not a very strong one, but if we treat this with diazomethane, CH2 and 2, the diazomethane, which is going to be this kind of structure, going to be a zwitterion. Okay, so it means positive, negative charge and a positive charge to be a neutral compound. Okay, so they coexist. So first this is going to behave as a base. Okay, so in effect, it's going to serve as a base, and then consequently turn this into a nucleophile and this into an electrophile, and I'll show you. So is this going to be the world's best nucleophile? Not particularly, but this is going to be a very strong electrophile. And you may be able to identify why. You have an N2 group as a leaving group. Pretty formidable leaving group, seeing as we have so much of it in the atmosphere already, right? And it's going to tug, that positive charge is going to tug electron density away from that methyl group. Remember that methyl is also going to be electron donating, to a slight degree. So in other words, we're going to form into gas irreversibly. Okay. So then we're going to get this methylation. And the irreversible part is quite important because you can actually do this in high yield. But if you are trying to do an esterification with alcohol and this, it's going to be kind of tricky because there's going to be very little energy barrier in terms of forming an ester versus a carboxylic acid and reverting. So just something to think about for next semester. Just this is going to be irreversible because, again, you're going to be forming N2 gas. And that's going to go up. Okay. So that is methylation of a carboxylic acid irreversibly. Okay, so next thing we're going to speak about is ethers. So symmetric and asymmetric. And there are a couple ways you can go about it. For symmetric ethers, you're going to want to use acidic conditions. Okay, so in other words, so for symmetric, acidic conditions. If you remember from your nomenclature, symmetric ethers are basically two R groups that are going to be identical left and right of a particular oxygen where that ether group exists, singly bound, of course. So if we, let's say, take two equivalents of isopropanol and treat it with H2SO4, we're going to get something like this. Okay. Or if we, let's say, take two equivalents of terbutyl alcohol, use H2SO4, we're going to get the equivalent, what we see above, just with two butyl groups. Okay, so what happens here is that this is going to behave as a base, pick up one of the hydrogens from H2SO4, protic hydrogen, and behave as a good leaving group. Then the second equivalent is going to come in and behave as a nuke and coordinate to that positively charged tertiary carbocation. Okay. So you can kind of get a mess from this if you go with an asymmetric ether and use acidic conditions, and I'll show you why. And I'll go through the mechanism so you can kind of deduce. Why it can get a little messy here. So problem 10.48. In your text on page 559. Okay, so we want to form this funky looking thing. Again, asymmetric because there's two different functional groups, or two different types of alkyl groups rather, about that oxygen single bonds on both sides. So let's try to basically disconnect everything and think about what kind of alcohols we would have here. So we would have 3-pentanol, and then cyclopentanol as well. Okay, so I'll just put this generically. Okay, so this is our target. Sorry, getting everything kind of scrunched up here. Okay, so now we have our protonated alcohol here. Dang. What am I doing? Okay, so a proton transfer has happened. Now, so it can go away and you can have a secondary carbocation. Okay, and then you could have two options. One in which you have this alcohol, again, cyclopentanol, act as a nuke, or another equivalent of this this 3-pentanol or pentane 3-ol that is going to coordinate right there. So in other words, there's going to be a competition in terms of what's going to react with that. Okay, so this is also going to be secondary if it were to split apart. So you're going to get a bunch of different mixtures. But let's just illustrate the mechanism in which we get this particular product, our target. It's going to react with secondary carbocation. And then remember, you're just going to be following a positively charged species throughout. Okay, and then something's going to behave as a base, one of these alcohols or water itself. Whoops. Way off course there, pal. Okay, so then we're going to have a stable product. Okay, so draw some products to see what you come up with the condensation with this. Alcohol attacking the carbocation. Try to get a carbocation out of that cyclopentane ring and see what you come up with there. Okay, so there's really a 50-50 shot of which one's going to connect to which. So you're going to get predominantly this product, right? But then you're going to have a little bit of some symmetric ethers as well. So something to take note of. Speaking of ethers, we're going to get into epoxide chemistry. But first thing, we're going to go about a simple way of producing epoxides. I'll show you in the next module how to prepare these halohydrin species. So halo coming from the halo group, and then hydrin coming from the hydroxyl. Okay. Now, if you have a strong base and you treat this under the presence of heat, say OH minus, okay, so it's going to be in equilibrium with picking apart this hydrogen here. Now, or rather, this anion is going to be in equilibrium with that OH. Remember, they're both going to be fighting for the same H plus. That H plus is the soccer ball. Right? Okay. So if we have lone pair that comes down is going to boot off that bromo group. Right? So it needs something to coordinate to that is slightly electron deficient. In this case, it's going to be that alpha carbon to it. Okay, so we're going to boot off a bromo group, and then we're going to have this epoxide as a result. Okay, pretty straightforward. Remember that three-membered rings are pretty strained in terms of bond angles and that kind of thing, and oxygen is electronegative. So something that we're going to get into next, which is epoxide reactivity. You can think of these as sort of being pretty reactive. So in other words, these bonds are pretty much free to break if you have strong enough conditions. Okay, so something I didn't mention about Williams and ether synthesis. If you want to get an asymmetric ether in high yield, so in other words, without wasting your product or waste materials making products that are not what you're targeting or intending. If you want to make this particular product, sorry to jump back here, guys, but thought it was pretty important, something I kind of glossed over here. You want to have a good nucleophile and a good electrophile, so you want to have some kind of control. Okay, now really the best way to go about this is to, instead of putting everything into one pot and cooking it in acid, let's say you make a nucleophile first. Okay, so you're going to use sodium hydride, which is going to be basic. Okay. So that H has 2 electrons or a lone pair about it. Okay, so it fills up that 1s shell. Takes this hydrogen irreversibly, right? Because, and this is an NaOH, just, this is going to be NaH if you blink for a second, okay? So NaH, as in nah, man. Okay, so hydrogen minus or hydride is going to take off that hydrogen, protic hydrogen that's here. These electrons are going to go onto this oxygen irreversibly, meaning that if you look at H2's pKa, it is wicked high, and it's going to go into the gas phase like a shot, right? It's going to be one of the fastest molecules that is going to travel about. So now we have this alkoxide anion, and if we have imagine just the disconnection here where you have a chloro group, so in other words something to tug electron density away from this carbon rather. We'll have a formidable leaving group, you have a formidable electrophile or electrophilic carbon, and then you're going to get your product specifically without any impurity. Alright, so chloro group's going to leave off Cl minus, right? It may form something with sodium, so you'll have sodium chloride and then H2 gas, which is going to go up. Okay. Alright, so I just wanted to go over that with you so you can see a better route for forming asymmetric ethers. So in other words, for the first step, these are going to be in two different steps here. So when you see a reaction arrow above NaH for step 1, step 2 is when you introduce your electrophile. Okay, so you don't want to have these in the same pot, if you will. The first thing you want to do is deprotonate completely and then introduce this. All right. Okay, on to epoxide reactivity. So let's take this particular substrate here. It's an asymmetric epoxide, and treat it under, let's say, acidic conditions. Okay, so this hydrogen is going to bounce off of this OH, but it's also going to bounce off this ether, cyclic ether. Remember, if this becomes positively charged, you have a bunch of alkyl groups that are attached to it to kind of stabilize that charge a little bit. So that's a little bit of a hint that you're going to get. Okay, so this is going to be positively charged. Oops. Okay. So which side is going to have electrons be pulled away from it more readily? So you don't have anything to stabilize a partial positive charge on this carbon because you just have hydrogens. And again, that's pretty much a baseline in terms of electron donating, electron withdrawing. This side you have electron donating, so in other words it would stabilize this having a partial positive charge. So this positive charge on the oxygen, the formal charge, is going to pull electrons away, so it's going to make this bond less stable. Okay. So in other words, even something that's weakly nucleophilic, like say methanol, it's going to attack here, and boom, open up that ring. Okay, so this is going to be positively charged. Okay. So this is going to be rather acidic. So we have water, which is from the first example. It's going to pick up that hydrogen. The electrons are going to come back to oxygen. We're going to have our stable product, which is going to be an ether. And there you go. Okay, so that's under acidic conditions. Okay. Now under basic conditions, so we have the same substrate. And treat this with methoxide anion, and of course the conjugate acid of that. Okay. It's negative charge. Remember, you're following positive charges for acidic conditions. Now you're going to follow negative charges for basic. Okay. So if this is going to be a good nucleophile, it has no place for it to go over here. Now you would think, oh, well, why doesn't this just, split off by itself, seeing as this is a protic solvent? It's a good argument, but in the end, this is going to attack the more accessible site. So in this case, it's going to be right here. so remain in acidic in basic conditions, because this will act as an acid to protonate and form your stable product. So this is going to be a tertiary alcohol with an ether group right there on the opposite end. Okay, so in other words, there's what is referred to as regioselectivity in the attacking group under different conditions. So this is under basic conditions. Just a reminder. Okay, so this is going to be an exercise, problem 10.53, epoxide ring opening again. So we have three different examples here. The first is going to be KCN, or potassium cyanide, in what is referred to as ethylene glycol. So this is typically what's used in antifreeze to depress the freezing point of water, right, or your coolant. And then you have lithium aluminum hydride for the second particular reaction. This is going to be example D. Notice how for the first example, or for the first step, you have lithium aluminum hydride. Second, you have H3O, and I'll get into lithium aluminum hydride in a second. But for the third, which is going to be example H, you're going to have CH3 Li. So this is going to be what's referred to as an alkyl lithium reagent. And then the second step is going to be H3O. So in both cases, this is going to be acidic conditions, but remember that each one of these steps is going to be a different physical step in terms of the process. Okay, not necessarily the physical separation in terms of location, what have you. Okay, so the first one should be pretty straightforward. Remember that if potassium is there next to cyano group, cyano or Cn minus is going to be electronegative. So let's just say that a lone pair from this carbon is going to attack. Remember, so it's going to be slightly basic and kick these electrons off. So something to pay note to the stereochemistry here, just so you don't get yourself mixed up. When I pop open the ring, I typically tend to put everything in that particular plane. Okay, so in other words, that cyano group is going to sit here at the bottom, kind of go in a staircase fashion. And then this is going to be used as an acid. So you're going to get sort of a cyanohydrin product here, albeit the cyano group and the OH group aren't going to be on the same carbon. You'll hear about cyanohydrins in the next semester. Okay, so that's the product you're going to get. Okay, so for D, the next example is going to be a little bit different. So we have lithium aluminum hydride, which is going to look like this. So lithium, it is going to be an ionic compound. So lithium is going to be the positive charge. And then aluminum, remember the aluminum is going to be in group 3A. So in other words, it is going to have a formal charge of -1 here if there's an additional hydrogen. So what this can really equate to is H minus. Okay. So in other words, this is going to be under basic conditions, right? So if H minus is here, H minus can act as a very, well, this is the equivalent of H minus rather. So you shouldn't necessarily just say, oh, well, this is going to be the representation of lithium aluminum hydride, which I almost did. This is actually going to be a powerful nucleophile, so it's not going to be as much of a base as it is a nuke. Okay. So where it's the opposite, where I showed you sodium hydride is going to be working as a better base. Okay, so this is also going to pop the ring open. But then the second step, you need to acidify, because you're basically going to get this without the cyano group, right? Instead, you'll just have a methyl group there. Again, because there's two hydrogens right there. Right? So the ring's been opened yet again. Okay, so then this basic species is just going to pick up a proton from H3O. Oops. Okay, and then you have your product. Okay, last one is actually going to be just as straightforward. You can just imagine what I did right there with this lithium aluminum hydride, and in substitute of just a hydrogen, like how I put over there, you're going to get. So this is going to be a strong nucleophile, the CH3 minus, right? So lithium is going to be positively charged, like it is right here. It's going to be much as straightforward as what we had in the last example. You just have a methyl group attached to that methylene carbon that was originally there. Okay. So that's it for ring openings. Just be aware that all of these are initially under basic conditions, at least. Okay, so these are basic epoxide ring openings, not acidic. Okay, the next thing I'm going to go over with you, so this is more of eliminations, this second, or these last two reactions that I'm going to go over here, or mechanisms rather. Okay, so this is not like anything you haven't seen already. So this is going to be, let's say, an E2 mechanism. So this hydrogen is going to come down, get off this bromo group, and then you're going to have this alkyne, which is not terminal. One of the things you want to pay attention to is the equivalence of NH2. So NH2 is going to be a very strong base. If you have it in more than one equivalent, that means if you have a dihalide, you can actually prepare an alkyne rather that way. So let's say we have 2,3-dichlorobutane, regardless of what kind of stereochemistry we have, because in the end, it's going to be a linear compound, right? So we'll say 2 equivalents. And of course, heat. Remember that heat is going to drive or push an E2 mechanism. So in other words, we have one elimination with this hydrogen right here getting kicked off. And remember, everything's free to rotate around. So in other words, things are bound to, especially in a high temperature, things are bound to rotate pretty freely. And you're going to get, this is your product. Okay. So in other words, what is it? 2-butine or but2-ine. Okay, so in other words, two two equivalents of Cl minus have split off, and you'll have two equivalents of NH3 there. One thing of note though, if this is, let's say, terminal, let's say we have this, you would need three equivalents of NH2 and heat. So that would be the first step. And then the second step, you would just want to treat it with water. The reason being is that if you had this under three equivalents of NH2, it's going to be highly basic, right? So, in other words, wrong. What you're going to have is an anion right here, okay? So, in other words, if you have that one hydrogen that's left here and it's still under basic conditions, it's going to get removed, okay? So, in other words, you're going to need to introduce some water on that second step to protonate and get your organic product. Okay. So this is going to be much more basic than OH is going to be basic. Okay, so that's what the reasoning is behind that second step of adding water. Okay, so that's one example of E2 mechanisms. Now we're going to get into anti-Zaitsev product generation. So this is going to go to alkenes instead of alkynes like you've seen. Just here. Same mechanism, different materials used. So the first thing to do is remember that an amine is going to be highly nucleophilic, especially in the presence of, say, a strong electrophile like methyl iodide. Okay, so if you have this in excess, again, I'm just going to write XS for excess. You have this lone pair that coordinates to CH3, boots off this iodo group. So do this 3 times, and then you're going to get a quaternary amine, which is just going to look like this. Okay, so that positive charge that's there is going to be tugging electron density away from this carbon. Now, we have 2 routes in which we could remove hydrogens once we introduce everything under basic conditions. So we would use Ag2O. Okay, so this would be O2 minus, which is going to be heavily basic. Okay, so we want a really strong base. We want to remove this hydrogen, but it's going to have to be anti and parallel, right? So it's going to have to be in that sort of staircase motif, if you will. And this is going to be, you're going to introduce this and then you're going to apply heat to eliminate. So what's going to happen is these silver ions, silver plus ions, are going to form a salt with I minus. Okay, so you'll form silver iodide, and then as a result you will eliminate and kick this good leaving group off. Okay, and this will be your anti-Zaitsev product. Okay, so it's going to be least substituted per your 2 options here. Okay. So this is not necessarily your most thermodynamically stable product, but in this particular instance, you have no choice. This is so sterically bulky, it's going to get in the way of any deprotonation happening, because this carbon that you see right here is free to rotate, right? But if it's going to be in the way, especially if it's going to bump into this this quaternary amine, it's going to be an issue. So this is the most accessible hydrogen, if you will. Okay, so this is a synthesis problem I'm going to go over with you real quick. Now, for a little added bonus, so you can see kind of multi-step multi-step synthesis, if you will. Sorry. Okay, so first step is to use LDA at low temperature. So remember that LDA is going to be a kinetic enolate forming base. So that is going to remove a hydrogen from this side. Okay. So in other words, you're going to have deprotonation at about this alpha carbon as opposed to right here. Remember that LDA is going to be bulky, so it can't really get into the where this space is readily. So it's much freer to get right here where there's an acidic proton alpha to the CO double bond. Second step, you're going to be introducing a formidable electrophile, which is going to be benzyl bromide, which is actually a lacrimate. I've used it before in the lab, and it will make you cry. And for some reason, it gives me this really weird kind of overdose of... Has anybody had like a weird stomach feeling after they drink something like cherry cola? It's like that, but about 1,000,000 times worse. I can't explain it. I do not ever want to use this stuff ever again. Okay, anyway, back to the transformation. So you're going to get an alpha alkylation right here with an enolate to form. And I'm going to just put things in shorthand here. Again, pH for a phenyl ring. Okay. Now our next step is methyl iodide in excess, followed by silver oxide, and then finally applying heat. So that's going to be an anti-Zaitsev formation. So you're going to form a vinyl group right there. So in other words, you're going to be eliminating this particular amine. Get this bugger. Okay? And then this next step, which is something you'll be seeing later on in the semester towards the end. This is what is referred to as a reducing agent. So this is going to be a hydride source, sort of like you saw before with lithium aluminum hydride. So when we did that ring opening with lithium aluminum hydride, that basically popped the ring open, right? So in other words, it acted as this hydride, if you will, is going to be acting as a nucleophile. But the best place that it can attack is right here at this CO double bond. So this is actually going to be the most reactive site of anything on here. Okay. Now, once that happens, that's going to kick these electrons up and over, right? So let's just say, okay, now I'm going to put that in quotation marks. H minus is going to attack, kick these electrons up. And then this is going to be the proton source. So you're going to get some R and S product. Right? You're going to get a racemic mixture. I'll put this guy here. Yes, Cat, we hear you. Okay. Now, we have an alcohol. We have H2SO4 and heat. Okay, so what's going to happen is this is going to form an actual ring formation, right? Because we have a vinyl group which is actually reactive. And this will kind of get you into chapter 11, which is going to be electrophilic addition, just to kind of give you sort of segue into it. This double bond that you see right here is going to behave as a nucleophile. When I say that, I mean it's really going to be more as a base picking up one of these hydrogens. Okay, so with that said, you're going to form an intermediate that's going to be positively charged. Okay, so let's say this just picks up a hydrogen, H plus. I know some of this is in a review, but I'm trying to do a little bit of a review on the top here and get you into some stuff that we're going to be seeing moving forward. Okay. So the most stable carbocation you're going to see since we can assume this is going to be under protic conditions, is going to be a shift over so it's going to be a hydride shift. Ooh, all over the place. Okay, so I'll just put tilde. This is going to attack. Okay, the stereochemistry may not be right on the money, but say since this is going to be under somewhat of water conditions, water is going to behave as a base here, pick up that hydrogen, and then you're going to have an epoxide, which is going to be oopsie, wrong end. Okay, so I know that was a lot. Just be mindful and don't forget about some of the things that I've told you about carbocation rearrangement for more stability, etc. We can go over this in the office hours if you wish, and hope this has been informative. Everyone have a good day. Thanks.